When the announcement came out of Beijing, it felt different. Not another routine observation, not another preliminary report. This was a verdict. This is the story of 3I/ATLAS, and what happened during the 36 hours the world went dark. The discovery. On July 1st, 2025, the Atlas Telescope network in Chile detected a faint, moving speck of light. At first, analysts thought it was just another comet. But within days, orbital calculations revealed something extraordinary. This object wasn't bound to the sun's gravity at all. Its trajectory was hyperbolic, open-ended. It had come from outside the solar system, would pass through once, and disappear forever. The object was officially named 3I/ATLAS, the third interstellar visitor ever observed, following the mysterious Oumuamua in 2017 and Borisov in 2019. Each of these rare bodies arrived without warning, streaking across the solar system at impossible speeds. To scientists, they were precious frozen messengers carrying chemical fingerprints from other stars. Early estimates placed 3I/ATLAS's heliocentric velocity at more than 209,000 kilometers per hour. The object was on a steep trajectory through the inner solar system, heading toward the sun's glare before it would sling outward again, toward the stars. But unlike its predecessors, 3I/ATLAS would reveal something we weren't ready to face. The strange behavior. As the weeks passed, telescopes across Earth locked onto the newcomer. Hubble took optical images. The James Webb Space Telescope analyzed it in infrared. Ground-based observatories from Hawaii to the Canary Islands recorded its changing brightness. But the data revealed something strange. Most comets brighten as water ice sublimates, turning directly from solid to gas when they approach the sun. But 3I/ATLAS didn't behave that way. Spectral readings showed that its coma, the diffused halo of gas surrounding the nucleus, wasn't dominated by water at all. It was carbon dioxide, CO2, glowing faintly through the vacuum. Water, the main driver of cometary activity in our solar system, was almost absent. That single fact suggested 3I/ATLAS had formed in an entirely different kind of environment, perhaps in the frozen outer regions of another star system. The James Webb Space Telescope and the SphereX mission detected a CO2 gas cloud extending hundreds of thousands of kilometers from the nucleus. The Hubble Space Telescope constrained the size of the nucleus, possibly as large as 5.6 kilometers in diameter, but potentially as small as 300 meters. Everything about this object screamed alien origin. And then, just as 3I/ATLAS reached its most revealing phase, its closest approach to the sun, Earth blinked. The blackout. In late September 2025, for 36 hours, nearly every major Western observatory went dark. Not because of catastrophe, but because of coordination, or the lack of it. Hubble paused for a scheduled gyroscope realignment. The James Webb Space Telescope began a planned instrument switch, a procedure requiring over a day of thermal stabilization. In Chile, the Very Large Telescope entered its maintenance cycle, its massive mirrors undergoing cleaning. Gemini North and Gemini South switched to pre-approved planetary studies. Each action, on its own, made perfect sense. But together, they created something rare, a global blind spot. The timing could not have been worse. During that exact window, 3I/ATLAS crossed a region of the sky perilously close to the sun's glare. Observing from Earth became nearly impossible without specialized equipment. With every hour unobserved, scientists risked losing critical data about its outgassing rate, coma evolution, and chemical composition. To the public, the pause went unnoticed. But to astronomers, it was devastating. A hole in the light curve of an object that would never return. Except, as it turned out, the sky wasn't silent everywhere. China's watch. Across the Pacific, China's high-altitude observatories in Tibet, Qinghai, and Yunnan kept watching. Their schedules, unaligned with Western institutions, left them free during the blackout. Their clear, dry air, thinner and colder than most sites on Earth, allowed continuous optical and infrared coverage. While the world's largest telescopes paused for recalibration, a network of smaller instruments on Asia's roof recorded the only uninterrupted data stream of the interstellar visitor. Each observatory followed a meticulous process. Light collected by their primary mirrors was focused onto cooled CCD sensors. Each exposure lasted between 30 and 120 seconds. At the comet's blistering speed, longer exposures risked motion blur. Every frame was time-stamped to within a millisecond using GPS clocks and stored in the standardized FITS format. These files were transmitted through fiber optic links to centralized servers in Nanjing and Beijing, where redundancy systems maintained power despite sub-zero temperatures. The engineers called them servers under ice. By the time Hubble and JWST came back online, 3I/ATLAS had already moved more than 1 million kilometers along its path. Without those Chinese data, scientists would have faced positional uncertainty so large that reacquiring the comet might have required blind scanning. Instead, China's observations allowed the rest of the world to realign. The data reveals the truth. The results were remarkable. Over the 36-hour blackout, 3I/ATLAS brightened by about 1/3 of a magnitude, a modest increase, but enough to indicate a spike in activity. Its coma elongated toward the sun, suggesting a jet of gas and dust erupting from the nucleus. Later analysis showed that the dust particles were unusually large and carbon-rich, a combination rarely seen in comets born within our own solar system. As the data circulated, it became clear that something profound had occurred, not just astronomically, but geopolitically. For decades, the world's great observatories, funded by Western consortia, had defined the boundaries of astronomical truth. Now, for the first time, the most critical observations of a historic interstellar event came from elsewhere. The instruments that mattered most were not the biggest or most expensive. They were simply the ones that stayed awake. Merging Chinese data with Western datasets required careful calibration. Brightness was calibrated using Landolt standard stars. Magnitudes were cross-referenced with the Sloan Digital Sky Survey. Spectral lines were corrected using thorium and neon lamps. Independent verifications by teams in Hong Kong and Taiwan confirmed the measurements within tight margins of error. Once combined, the global dataset reached unprecedented precision. Astrometric accuracy within 1/5 of an arcsecond, eccentricity fixed at 1.19. The verdict was irrefutable. 3I/ATLAS was an interstellar object. The uncomfortable truth. But beyond the numbers, the event highlighted an uncomfortable truth about modern astronomy. For all its talk of international cooperation, the system remains uneven. Of the world's 30 largest telescopes, those with mirrors over 6 meters in diameter, 2/3 are located in the Americas or operated by Western partnerships. China's telescopes are smaller, typically between 2 and 4 meters, but their strength lies in automation and distribution. Multiple mid-size instruments working in tandem can outperform a single giant one when timing and coordination matter more than sheer sensitivity. Large telescopes are designed for depth, to peer into the faintest galaxies billions of light-years away. But smaller observatories excel in continuity, watching the same patch of sky hour after hour. For transient or fast-moving targets like 3I/ATLAS, that constancy can be more valuable than aperture. During the blackout, China's robotic scheduling software reassigned telescopes in real time as weather and target angles shifted. By stacking hundreds of short exposures and co-adding the data statistically, the network achieved a signal-to-noise ratio rivaling that of much larger Western instruments. Persistence, not size, became the decisive factor. When the final combined analysis was released, the language was careful but unmistakable. The data confirmed that 3I/ATLAS was composed primarily of carbon dioxide ice, that it had originated outside the solar system, and that it passed through on a one-time trajectory before heading back into interstellar space. But there was something else beneath the surface of those conclusions, a recognition that the discovery marked a turning point. For decades, the Western scientific community had been the unquestioned keeper of cosmic truth. Now the chain of observation was global, and the links had shifted. A single blackout had shown how fragile centralized knowledge can be. China's final report closed on a line that sounded less like science and more like reflection. Nothing about the object has changed, and yet everything has. It was a statement about the comet, but also about us. The discovery had not revealed aliens or danger or hidden messages in the stars. It had revealed something subtler, and perhaps more profound, that the boundaries of exploration are shifting, that truth in science now depends on shared vigilance, and that the universe continues to speak in signals we can only hear when someone, somewhere, refuses to blink. For 36 hours, half the planet looked away, the other half didn't. And in that narrow window, humanity's newest messenger from the stars whispered its story into the record, unseen by most, but not unheard. A fragment from another sun passing through ours, carrying the quiet confirmation that we are far from alone.